So some of what we're going to go over in the following lecture is a bit of a review going from Psych 220 to Psych 221, but it's important for us to make sure that we're secure and really firm in our understanding of these concepts as we move forward. As starting on our next lecture, we're going to start talking about actual statistical techniques. So this is going to be pretty much the last of kind of the theory or methodological slides for a while. And I really wanted to just kind of review in general the process of creating hypotheses, the importance of hypotheses, and how we logically test those hypotheses using the statistical techniques that we're going to discuss in this class. So there is a divide between your hypotheses, the previous literature, and the logic of what you're examining in a study, and the actual statistical analysis to determine whether that hypothesis is supported or not. However, the framing of the hypotheses will help determine the appropriateness of the statistics, and the statistics then will determine if you can actually support or not support that hypothesis. So let's dig into hypotheses again, our final review, really taking a look at exactly how these fit and interact with the actual methodologies we use to test them. So again, hypotheses definitionally are predictions about specific events, and these predictions are often about the causal relationship between two or more variables. So at their most basic level, a hypothesis is simply a logically theoretical statement which makes a prediction about events or occurrences. In other words, it basically predicts patterns, it predicts relationships, it predicts a statistical significant effect, if you will. But it's stated in such a way that our lit review supports those hypotheses. In other words, we're not coming up out of thin air. We have a reason to be looking at these hypotheses. We have a reason to state these questions. And the questions are worded in such a way that they can be examined and either proven or disproven by the study we then suggest. And the hypotheses are the drivers behind our methods and our statistics. The whole reason we do a lit review is to build up the logic and theory behind the hypotheses, the specific testable questions that we want to examine in our study. And each hypothesis should be a distinct prediction about a specific event, and those predictions tend to be causal in most studies. And what I mean by causal is kind of the goal of science is to be able to identify variables that predict each other, variables that are causing each other. If I know that a particular predictor, for example, room temperature, impacts your aggression, it gives me a lever in the real world to try to reduce or increase behavior. If I'm wanting to increase the likelihood that people will be aggressive, I want to make sure they're in a hot environment. If I want to decrease the chance that they're going to be aggressive, I'd want them in a cooler environment. So that doesn't give me complete control over people's behaviors, but it does allow me to start to think about how do I set up situations where positive behaviors are more likely and negative behaviors are less likely. And this can be everything from at a society level to a personal level. For example, we know that setting clear, moderately difficult but obtainable goals typically increases the chance of you doing the behaviors necessary to get to the goal. So again, that doesn't tell us solely what is going to be the only decision of whether you attain a goal or not. Do you set one? However, setting one and the type that you set. So example, we've actually researched and found that very easy goals are actually less likely to be acted on, and very difficult goals are less likely to be acted on. It's usually a moderately difficult goal, something that may stretch you a little bit, and how much it stretches you depends on the individual. So again, when we talk about causation and causal, we're not just trying to get it in some kind of eye in the sky concept. We're really trying to look at, can we trust these studies to help us actually change the real world? So for instance, if we're wanting to reduce the likelihood of people behaving violent in groups, we know that basically identification is one of the best things you can do. People are much less likely to engage in mob behavior if their faces can be seen and they're wearing name tags. Those two adjustables basically greatly reduce the chance of any kind of mob action. Now, how can you actually do that can also be a practical issue, but also we usually find that in situations where we see the worst behavior in kind of mob settings, it's usually when people feel like they cannot be identified interpersonally. Either they're wearing masks, they're covering their faces, and there's no way to tell who they are. We're much more likely to act upon, shall we say, more base instincts. So again, when we're creating hypotheses, though there are some scientific hypotheses that are purely about just learning about how the world works, a lot of the times in psychology, we really are trying to find antecedents. So those are predictors. Those are things that come before, that then may be used if we find the relationships we're interested in finding on further behaviors to either increase or reduce those behaviors. So causal hypotheses are statements of relationship between an independent and dependent variable. They describe a cause and effect, and they're usually stated in two forms: the null hypothesis and the alternate hypothesis. And generally, when I say they're stated in two forms, the null hypothesis is usually not stated, but if you can't create a null hypothesis off your alternate hypothesis, you have a problem. In other words, every hypothesis needs to be either provable to be right or provable to be wrong. So if I have a hypothesis that no matter how my study comes out, I can still make an argument that that hypothesis is supported. A lot of psychoanalytic hypotheses about the subconscious are this way. Well, if you found it, it's because it was there. And if you didn't find it, it's because it's hard to get to the subconscious. Well, that's not a testable causal hypothesis. Our hypotheses need to be stated in such a way that if the results find the pattern I expect statistically, I say I've supported the alternative hypothesis. And if they don't, I've supported the null hypothesis. Basically, the unspoken statement that my hypothesis is wrong. And these two forms should be mutually exclusive and exhaustive. So mutually exclusive means that you can't prove both at the same time. Either one or the other is proven. Now, where this comes up most when you're wording your hypotheses is that if you have a hypothesis that has multiple factors in it, for example, if you're basically saying, I hypothesize that anxiety and depression are both predictors of life outcome. In order for that to be supported, you would have to find statistical significance in both depression and anxiety. If you found one or the other, that's the null hypothesis, because you stated a hypothesis that basically says I have to find both for this to be proven right. And that's what mutually exclusive means, that the hypothesis in an alternate form has to be either fully proven, and if any portion of it is disproven, then the null hypothesis is supported. It's one of the reasons in a lot of studies you'll see hypotheses broken up into hypothesis A, B, C. So for example, instead of saying anxiety and depression are related to life satisfaction, I could say hypothesis 1A, anxiety is related to life satisfaction. Hypothesis H1-2 or B, depression is related to life satisfaction. And then I might even have an H1B or C3, which basically would say, however, the stronger relationship will be when someone is depressed and anxious. Each one of those is a separate hypothesis. Each one has an alternate null, but in this case, I'm no longer having to rely on the entire combined hypothesis being supported or not supported. Each hypothesis should also be exhaustive. There should not be leftover possibilities that we don't include. They should either be what we're stating or not what we're stating. So basically, this is a guideline or a way to kind of test, are your hypotheses getting too complex? And if so, the answer is usually to break them down to where each hypothesis has an alternative and a null, they're mutually exclusive, and they're exhaustive. So hypotheses will often look like it's expected that an independent variable will cause an increase in a DV, or it might be hypothesized that IV will be related to a DV. And we've already kind of hit this, and that's again that when we talk about cause, that basically says that unless I actually establish causation in my methods, then at best I'm going to be able to argue the possibility of cause, but I can't actually say there's truly a cause. I'm going to have to basically say that there was a relationship of an increase, but I don't know if it's a causal relationship. However, I may also simply hypothesize that there's not a directional relationship, that there'll be one in general. And again, we've talked about this as far as the one and two-tailed hypotheses and the advantages and disadvantages of each of these, and I'm going to go into that a little bit more in this lecture. So again, hypotheses can be the null hypothesis, basically the hypothesis predicting no relationship between variables or no effect of one variable on another, or in the case of an alternate hypothesis, the directional, if you even find the other direction. So if I expect an increase and I find a statistically significant decrease, I've still supported the null hypothesis. my data did not support my alternate hypothesis that there would be an increase. It either basically supported that there was no relationship, or that the relationship went in a direction that I didn't predict. So when we do create a directional hypothesis, though directional hypotheses are more powerful at finding an effect in the direction we're stating, we do want to make sure that it is logical, literature review, and theoretically appropriate to make a directional hypothesis. Because when we do make a directional hypothesis, we're actually somewhat strengthening the potential of the null hypothesis being supported. So again, our alternative hypothesis is one that's predicting a relationship, and we may either state a relationship in general or a directional relationship. And if it is a directional relationship, basically it is a hypothesis, a one-tailed test, expecting a particular direction. So again, group 1 would be greater than group 2, or group 1 will be less than group 2. But we specifically state that in our hypothesis, which again means our alternate hypothesis is only supported if not only we find a statistically significant relationship, but it's also in the direction we expected. We can also do the non-directional two-tailed test, a hypothesis just predicting any relationship or effect. In other words, group 1 will differ from group 2, and based on past theory, based on past literature, I really am not sure which way this is going to go, but I do believe there's going to be a relationship. Now, the advantage here is that if you now find a statistically significant relationship in either direction, you have supported your hypothesis, and you're only rejecting it, in other words, supporting the null hypothesis, if there's no relationship. The problem, though, here is that the amount of difference in either direction has to be larger for you to be able to claim statistical significance. So like most things in research methods and statistics, there's always trade-offs, positives and negatives, with every decision you make as far as the methodology, even the wording of your hypotheses, and then the statistics that you use. So again, what we're talking about within hypotheses is a hypothesis is going to lead us to a specific set of statistics through our method section. And the statistics that we're using whenever we're actually comparing groups or looking for relationships is inferential statistics. And again, the word inferential means here that I'm inferring from my sample to the population. In other words, all inferential statistics aren't just looking for a statistical relationship or a mathematical relationship between variables. They're also looking to make a conclusion about the population from the sample. We have to infer the nature of the population from the sample. And again, this is why it's so important to really have a good idea of what is your population, what's your sample frame, how much of the population do you even have access to, and then from within that population frame, how much sample can you actually draw? What does your sample look like? We always have to consider sampling error. We have to consider the nature of the error that occurs in this process, increase power to reduce the impact of that error. And increasing power in this case usually means the larger the sample we have, generally the more representational it is, but obviously also the more time it takes to gather the data, and maybe even more resources depending on how much each person going through the study costs us in both time, resources, and energy. So within an inferential statistic, when we're testing a hypothesis, we're going to use it to infer the results based on the sample to the population. We're basically saying, did we support or refute the alternative hypothesis in this sample? And then if we did support the alternative hypothesis in the sample, how likely is it that we would find that effect over and over and over again if we kept rerunning the study on different samples? And it's usually an estimate based on that sample size. So we're comparing the obtained test statistic, that's the value we actually gather from running our mathematical equations, to a test statistic probability distribution. And we compare the critical test statistic to the minimum value required for the alpha level, or P, that we're looking for. Now remember that the test statistic probability distribution is specific for each test. There's one for correlations, there's one for t-tests, there's ones for ANOVAs. And they're based on what is the value that you would have to obtain in the mathematical calculations for you to be 95% sure that that effect would be found over and over again in the population. So just remember that at the end of the day, not only are we getting the strength of the relationship and the mathematics of the relationship, we're also getting what's most important to us, our probability estimate of how likely is this effect, this relationship, due to a systematic difference that we found in our sample that we would also likely find over and over again in the population. The less likely that is, the less likely we are to claim statistical significance. So a statistically significant difference is any difference between groups that is due to some systematic influence and not due to chance. And therefore, a statistically significant relationship is any relationship between variables that is due to some correlation between those variables and not due to chance. And again, it's estimating what is the likelihood that we would find this over and over again if we did run additional studies with similar samples drawn from the same population. So our criteria for determining statistical significance is the risk associated with not being 100% confident that what you observed in an experiment is due to the treatment or a correlation between the variables. We have set that, and that's referred to as the alpha level, at 0.05, a 1 in 20 chance, or a 5% chance if you want, to basically accept the hypothesis. In other words, we accept the alternative hypothesis is true only if we're 5% or less likely of being wrong. So we've basically kind of tipped the bar, if you will, to where 95% of the time when we find an effect, if it isn't strong enough for us to be more than 5% sure or less than 5% that we think we're wrong, in other words, we have to be 95+% confident that we're right, we are not going to actually report it as statistically significant. Now, this is a fairly high bar, but it's a high bar based on the idea that we would much rather miss an effect, assuming that other people are going to be looking for the same effect, because science is an iterative process. Iterative just means that people are constantly running new studies. Undergrads are running studies, graduate students are running studies, so a lot of ideas are being tested multiple times. And we really just want to make sure that before we actually start to tell the world about, hey, we found a meaningful relationship that we think you can use in your therapy, in your organizations, or even in your civilizations, or even in your personal life to make your world better, to increase positive behaviors and decrease negative behaviors, we want to be pretty sure that we actually found it and that it's there and it's a real effect.